All right, so in this section, we're going to find polynomial functions that could be used to approximate transcendental functions. A transcendental function, we're talking about functions uh, that cannot be described with normal algebraic functions like multiplying, dividing, timesing, adding, subtracting. So, for example, a polynomial is not a transcendental function, but one that is like e to the x or a logarithm. Any of those types of functions that can't be represented with those normal algebra functions. All right. So anyway, we're going to look for polynomial functions that you can use to approximate those transcendental functions. So it says if p of x is a polynomial function used to approximate some other function f of x, they must contain the same point with the same value c. So right there, that's important. They must contain the same point with the same value c. We'll see that here in just a second. So in other words, at c, when you plug c into the polynomial function, you get the same thing as when you plug c into the actual function you're trying to approximate. To better the approximation, they should also have the same slope at that point. Well, if they have the same slope, that means that the derivative of the polynomial function at c is equal to the derivative of the function at c. And if you want even more accurate, we want the second derivative to equal the second derivative of the function at that point. Anyway, so when you put all this together, we end up with what's called the Taylor polynomial expansion. Okay, and this is what it says. It says, if f of x has derivatives of all orders, it could be approximated by the polynomial function shown below. Okay, so this right here, this is the polynomial function. And we can approximate, the way we find it is, right, I do f of c. Okay, so what is the function equal to at c? What is the first derivative equal to c times x minus c? What is the second derivative of c divided by 2 factorial times x minus c squared? What is the third derivative at c over 3 factorial times x minus c cubed, and so on. So this is called the nth degree or the nth order Taylor polynomial centered at c or expanded about c. Okay, so the big idea here, right, is we're coming up with a function that approximate a polynomial function, excuse me, that approximates another function. Okay, and this is a formula to come up with that. All right, what if you put the center at 0, like we talked up here, right? Talked up here about, about that value c. Okay, that's the center. If we put the center at 0, we can simplify the function down quite a bit, right? If I plug 0 for c, so 0 there, like all the way through here, right? I'm just putting zeros in for c. Then we end up with what's called the Maclaurin polynomial, which is down here, right? P of n of x is equal to f of 0 plus f prime of 0 of x plus f double prime 0 over 2 prime. So basically just replacing all those c's with 0. Now, this n down here, what it's talking about is the further you go out, the further you expand out these Taylor polynomial expansions, the further you go, the more accurate it will be. And we'll show you some examples of that. So this one says, use the formula for a Maclaurin polynomial to find the 5th degree Maclaurin polynomial for f of x equals e to the x. So when it says 5th degree, what it's talking about, right, is it's going to be like this, p, and that means n is 5. That's how far I have to go out right there. Okay, so we're just going to plug it in that formula up there. So we're going to, and this is for e to the x. So let's go ahead and fill this out. F of x is equal to e to the x. The derivative of e to the x is still e to the x. This is pretty easy because as I go down, right, derivative of e to the x is e to the x. So when I plug 0 into all those, right, e to the 0 is 1, e to the 0 is 1, all the way down. Now, this will make this one pretty easy to do. Okay, so when I set this up, I take what is f of 0? That's right here. So 1 plus f prime of 0 times x. Well, f prime of 0 is 1 times x would be x. Plus, okay, and I do the f double prime of 0, which is still 1, over 2 factorial times x squared, plus Again, the third derivative is also 1. This will be 1 over 3 factorial x cubed plus 1 over 4 factorial x to the 4th plus 1 over 5 factorial times x to the 5th. Okay, so there's the 5th degree Maclaurin polynomial. And what that does is it gives me a close approximation to the function f of x is equal to e to the x. So that's the, right, this is the answer that should go right down here. It's putting up above. So it says this polynomial is a good approximation for f of x equals e to the x, but by extending the pattern out to an infinite series, it actually gives you the exact correct instead of the approximation. So it would actually, so this is an approximation, right? And it's actually a pretty good approximation to e to the x. But if we expand it out, we can get the exact value. Well, in fact, what it means by that is just expand it out. So I have my first, my second, my third term, oops, got my factorials on there. Got, just keep going, dot, 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 plus. And we can see the pattern here, right? So when I'm on my third term, I get 1 over 2 factorial. So I'm going to come out here. It's going to be x to the n factorial over n factorial. And just see if that works really quick. So for example, if I plug 2 in for n, I get 2 to the n, or sorry, I get x squared over 2 factorial, right, which is that one right there. If I plug 0 in, I get x to the 0, which is 1, over 0 factorial, which is 1. If I plug 1 in, I get x to the first, which is 1, over 1 factorial, which is 1. If I plug 3 in, anyway, so you can see that it fits. If I plug 3 in, I get x to the third over 3 factorial. So if we make that an infinite series, okay, then that actually gives us the exact value of e to the x. So what happens here is if we take the general form of the Taylor and the Maclaurin polynomials and we extend them out, we end up with these series. So here's the Taylor series. Now, this only works if f of x has derivatives for all the way down, for all orders. Okay, or the Maclaurin series, same thing. So if I look at it, all I'm doing is all I'm adding on there is I have to extend it out to infinity. Like it has to keep going on both of these. So these formulas allow us to find power series for functions that can't be written as a geometric power series. Like back in 9.2, we just went through those geometric power series. So these are not geometric power series, but we can find a power series that still equals or is equivalent to these functions. Okay, so let's go through and let me show you one of these. So it says use these formulas from the Taylor polynomial to find a fourth order Taylor polynomial and Taylor series for f of x equals cosine of x at c equals pi. Okay, so it wants me to find, these are two different problems, right? It wants me to find the fourth order Taylor polynomial, and then it wants me to find a Taylor series, which means that we want it to go to infinity. Okay, so let's see if we can come up with this. Instead of doing it down below, I'm going to draw off the side, and maybe we can see, we can shrink this down a bit and see what's happening up there. So first, let's fill this out first. So if f of x equals a cosine of x, the cosine of pi is equal to -1. The derivative would be negative sine of x. Okay, if I plug in pi, I get 0 into the sine of x, negative sine of x. The derivative of negative sine of x is negative cosine of x. If I plug in pi, I get 1. It's like a negative 1. Derivative of negative cosine of x is sine of x. If I plug in pi, I get 0. Derivative of sine of x is cosine of x. And if I plug in pi, I get -1. So that's what we need to do the fourth order Taylor polynomial, right? Okay, so I'm going to shrink this down a bit so we can see it up above. Okay, I'm just going to start plugging things in our formula up there. So I'm going to say this p fourth degree polynomial, Taylor polynomial. It's going to look like this. First of all, I take f of pi. That's this f of pi right here is -1 plus, okay, and then I take f prime of pi, which is 0, times by x minus c, which is pi. Okay, just keep going to the next one. Right. So take f double prime of pi, which is 1, over 2 factorial, times x minus pi squared. Again, I just plug these numbers in the formula. Okay, take the third derivative of pi, which is 0, 0 over 3 pi times by x minus pi to the third, plus, okay, the fourth derivative of pi is -1, so -1 over 4 factorial times by x minus pi to the fourth. Okay, there's my fourth order Taylor polynomial. Okay, and that will give us a pretty close approximation of what the cosine of x is for any numbers that are close to pi. Okay, the second part says it wants us to come up with a Taylor series, and this gives us the exact value. So in this case, it's going to be the same thing, but it has to go to infinity. Now we can do a lot of simplifying, so I'm going to do a lot of simplifying up above. So I have f of x equals, I got -1, right? Some of these, this, because I'm timesing by 0, and this because I'm timesing by 0, if you went out x to the 5th, it would come out to be 0. They're just going to go away because of that. Okay, so that part, those highlighted parts went away. So I have plus. I'm just going to combine those together and make it a, well, actually, it's, yeah, plus. I'm just going to write it as being x minus pi squared over 2 factorial. That's this part right here, right? This next one's going to be a minus. So minus and x minus pi to the fourth over 4 factorial. And we could follow this pattern. The next one's going to be a plus, and it's going to be x minus pi. Even though we don't have it written up there, we can follow the pattern over 4 factorial. Okay, and that's just going to keep going that direction. Okay. This example number 3 says use your Taylor approximation from example 2 to approximate the cosine of 3. So you'd grab a calculator and you're going to plug 3 in for all the x's, right? Let me get a different highlighter up there. So we're going to come along here and we'd plug 3 in there, plug 3 in there, plug 3 in there. And then, let's see, it wants us to use, it actually wanted us to use just the 4. So we would actually just use, we would stop right here. Okay, and plug that in a calculator. I'm not going to take the time to show a calculator or anything, but when you do that, you plug that in, it comes out to be a -0.98987. Well, if you plug it in the calculator, interesting enough, you can plug in the cosine of 3. It comes out to be -0.98999. So you can see how accurate that is. Right, pretty cool. And that was just the 4th degree, right? That was the 4th degree Taylor polynomial. The further you go out, the more accurate it's going to get with these approximations. So kind of cool. So I think it's pretty cool. Hopefully you think that's cool too. Okay, let's look at this next one. Just use the formula for a Maclaurin series to find the Maclaurin series for f of x equals a sine of x. So we want to fill out this little chart. We've got to do enough so we can come up with a pattern here. So let's see if we can do that. So we can go, let's see, if f of x equals a sine of x, f of 0 would be 0. Derivative of sine of x is cosine of x. If I plug 0 in there, I get 1. Derivative of the cosine of x is negative sine of x. If I plug 0 in there, I get 0 still. Derivative of negative sine of x is negative cosine of x. You guys go ahead and pause the video, fill out the rest of that. Should have come up with this, right? Sine of x, cosine of x, 0, 1. Okay, I want you really quick to try. Take the formula we have up there in the book for a Maclaurin. Now we're doing a Maclaurin series. Okay, not a power function. Not a power function, but the series. I want you to pause the video and see if you can write out. Go at least 4 or 5 terms. Okay, just writing out the Maclaurin series, and then come back and I'll do it, and you can kind of compare it with what I end up with. Okay, should look something like this, right? When we plug in there, we get 0 plus 1x plus 0 over 2 factorial x squared plus negative 1 over 3 factorial x cubed plus 0 over 4 factorial x to the 4th plus 1 over 5 factorial times x to the 5th. And we could keep going there. Let's simplify that down. I'm going to write it up above. So f of x would be equal to, right, just x minus x cubed over 3 plus x to the 5th over 5 factorial minus 7, or x to the 7th, sorry. Let me just fix that, sorry. X to the 7th over 7 factorial plus. Now this is a tricky part. I want you guys to actually try this. Can you write a formula to come up with the nth term for this? So this is the first term, second term, third term, fourth term. Can you come up with a formula that gives you the nth term? So pause the video for a second and see if you can come up. This one's a little bit tricky, but I want to see if you can figure it out. All right, let's compare here. So the first, you notice first of all that it's alternating from positive to negative. That means I need it times by a -1 each time. The question is, I want the first term to be positive. So if I put an n there, the first term would be a -1, it would be negative. So I'm going to make it an n minus 1. Then when I plug in 1 for the first term right here, right, this is the first term, I'd get 1 minus 1 is 0, -1 of the 0 is a positive 1. If I plug in 2, that'd give me that one. It'd be 2 minus 1 is a -1. -1 to the, sorry, 2 minus 1 is 1, but -1 to the first is a negative. 3, I get -1 squared would be a positive. So that should give me, by making that -1 to the n minus 1, that should give me that alternating pattern. The other tricky part is the powers are going up by 2 each time. So on top, I want it times x. And I want it to be 2n because it's going up by 2. But here's what I have to be careful with. If I plug in 1, I get x squared. If I plug in 2, I get x to the 4th. If I plug in 3, I get x to the 6th. So I want to put a -1 on there. Now see what happens. When I plug in 1, I get 2 times 1 is 2, minus 1 is 1. Right? My second term, 2 times 2 is 4, 4 minus 1 is 3. My third term, 2 times 3 is 6, 6 minus 1 is 5. Okay, then down the bottom, I need this should have been a factorial here. Sorry about that. 3 factorial, 5 factorial, 7 factorial. So again, it's going up by 2 each time. And notice how the factorial matches the top number. So I can do the same thing. I can do that 2 minus 1 factorial. So just try it really quick. That's really over 1, right? If I plug in 1, I get 2 times 1 is 2, minus 1 is 1. Plug in 2, 2 times 2 is 4, minus 1 is 3. Plug in 3, I get 5. So that should give it to me right there. So that gives me the formula for the nth term. But when you come up with a series, like the series means it goes on forever, right? You keep adding those. And this would give you the exact value. That is a series that is equivalent or equal to the sine of x. Okay, it gives you the same thing as the sine of x. Okay, let's try this last one. It says find a power series for f of x centered at c equals 1. Hey, when I see that c equals 1, that means it's got to be the Taylor power series, right? Because the Maclaurin has to be at c equals 0. And it tells us that f of 1 equals 2, and f of the nth derivative of 1 is equal to n factorial. So in other words, if I want to write this down, what that means is let me grab the me grab the pen instead of the marker there. What that means is if I plug in f prime of 1, that equals 1 factorial. If I plug in f prime of 2, that equals 2 factorial. If I plug in f prime of 3, that equals 3 factorial, and so on and so forth. That's what that part right there is talking about. Okay, let's see if we can come up with this. So grab your formula for, we know this is the Taylor series, and again, the reason why is because that is not equal to 0. Okay, so let's plug this in here. We're going to go f of x equals, and I just take f of 1. It tells us f of 1 is equal to 2 plus 1 times x minus 1 plus 2 factorial over 2 factorial times x minus 1 squared. I'm just plugging those numbers in that formula. I know I don't have it down here. You have it there on your paper. Make sure you're looking at it. Okay, plus 3 factorial over 3 factorial times x minus 1 cubed. Now we could keep going, but hopefully the pattern here is pretty apparent, because what's going to happen is these are just going to reduce, right? Those are going to reduce, those are going to reduce, and we end up with this. I end up with a 2 plus x minus 1 plus x minus 1 squared plus x minus 1 cubed plus ... Okay, so let's see if we can write this as a series. This is a little trick. Remember, when you're writing out a series, you're just adding them together. So that 2 plus, I'm going to move it out in front and go 2 plus, and that way I can start with n equals 1. So now I'm starting right here. And that makes it really easy because all I have to do is just go x minus 1 to the nth power each time, right? That's x minus 1 to the first, x minus 1 to the second, x minus 1 to the third. So by moving that 2 out, it makes it a lot easier to write this. So this, right, f of x equals this. This is equivalent to the function f of x up there when it's centered at c equals 1. Okay, so again, what we're focused on is coming up with those polynomials and then the series where we're with the polynomials, you're approximating those functions using a polynomial function. Okay, and then with the series, right, instead of getting an approximation, now you're actually getting the exact value, right, instead of the approximation anymore. All right, good luck.